Let us start the lecture. In this lecture, we are going to discuss about the alternating current. Before going through alternating current, first of all, we have to discuss about the direct current. In direct current, we have these two types of figure. Let us discuss the first figure. In first figure, we have one resistor is here and one battery of potential V is here. So, in this battery, we have one positive terminal, one negative terminal is there. In direct current, current always flows from high potential to low potential, that is from positive end to negative end. It's always, that means the direction of current is always same. If we give 10 volt of potential, then it gives always 10 volt. It never be 9 volt, 11 volt, or whatever it may be. It's always 10 volt. That means its magnitude also same. In second figure also, here we have a resistor R here and potential V here. Here we just change the polarity. In right hand side we just take the positive and in left hand side this is negative. And in this figure current flows from right to left. In the first figure current flows from left to right always, and in the second figure current always flows from right to left. It never be from left to right. That means in direct current the magnitude is always constant and direction is also same. So, but in case of alternating current, magnitude changes continuously and direction changes periodically. That means the here. This is the graph for alternating current. In y-axis we have current and in x-axis we have time. That means here time dependent current. Current changes with respect to time. Just here, this one is our magnitude of current. This one also magnitude of current. That means current changes with time. If time changes, then magnitude of current changes. That means current magnitude of current changes continuously with time. And periodically reverse direction means for here we have one complete cycle, that is from this point to this point. Yeah, complete cycle, yes or no? For positive half cycle, this is our positive half cycle. Current, if in positive half cycle current flows from left to right, then for negative half cycle current flows from right to left. Yes or no? That means direction changes periodically. For first half cycle, direction from left to right, or it may be from right to left, or in negative, or in second half cycle, current flows in reverse direction. So, this is actually our alternating current. We can write alternating current I as I naught sine omega t. Here I is our instantaneous current. That means current at any instant t. This I naught is our peak value. That means this is our maximum value of current. Maximum value of current. This is our I naught. This point I naught, and this is our negative I naught. This is the maximum current, peak value. This omega is our angular frequency, and omega can be written as 2 pi upon t, or you can also write 2 pi nu or 2 pi f. Nu is our frequency, and this capital T is our time period. This omega t is called phase. This omega t is our phase. This is called phase. This is the formula for alternating current. Then what about alternating EMF? For alternating EMF also, in y-axis we can take the EMF, in x-axis we can take the current. Sorry, time. Here also we can write E equal to E naught sine omega t. In direct current we have, if we have to take the battery as 10 volt, then it gives always 10 volt. But in case of alternating current we can get different value of potential. That is, if we take the maximum value of EMF is 10 volt, then you can get the EMF value from 0 to 10 volt. Okay. Here also E is our instantaneous EMF, E naught is our peak value. This omega t is called phase, and omega is our angular frequency, t is at an instant at any time t. Okay. Before going through the chapter alternating EMF, we have to remember these few integrations. First of all, just remember this one: integration of sine or cos over complete cycle. T is our time period. Okay, time period means time taken by the alternating current or EMF to complete one cycle, one rotation. So the time taken by the alternating EMF or it may be alternating current to complete one cycle. And if we integrate sine omega t or cos omega t over a complete cycle, then we can get zero value. Okay, but if we integrate sin omega t over a half cycle, then you get t by pi. You can do this. And for complete cycle, if you integrate sin square omega t, as you know, so sin square omega t can be written as 1 minus cos 2 omega t by 2. Yes or no? From where we got this formula? As you know, cos 2 theta equal to 1 minus 2 sin square theta, or you can write 2 sin square theta equal to 1 minus cos 2 theta, or this sin square theta becomes 1 minus cos 2 theta upon 2. Yes or no? If we integrate this, then we can get t by 2. You just have to remember this one. Then we have average value of AC over a complete cycle. As you know, we have average value AC means alternating current. So for alternating current, we can write I equal to I naught sin omega t. Yes or no? But we have a formula. I can be written as dq upon dt. Yes or no? Or we can write dq as I dt. In place of I, just write down I naught sin omega t. Then total charge over complete cycle. We can get, for this we have to integrate the above equation. This is integration of dq. Here I have to put 0 to capital Q. Okay. Then on RHS side, I naught sin omega t dt. Just see here. Here we have dt term. So we have to take the integration limit from 0 to capital T. That is for complete cycle 0 to capital T. And we know I naught is our peak value which is constant. So we can take outside, and then integration of 0 to t sin omega t. Yes or no? Dt. As you know, integration of sine or cos over a complete cycle is 0. So here you can write this left side integration becomes dq is q, that is from 0 to q. Here you can get capital Q minus 0, or you can write q also. Q equal to I naught into 0. Right? Because the integration of sine or cos over a complete cycle is 0. Then our q becomes 0. Q0 means current over complete cycle. I equal to Q upon, for complete cycle we have to take time capital T. If you have half cycle, then you have to take the time T by 2. Here you have full cycle, so we take the time, this is our capital Q by T. Capital Q by T. Capital T is for complete cycle. Okay. And as Q is 0, so here you can get I is 0. That means for average value of alternating current over a complete cycle is 0. Okay. If over a complete cycle is 0, then we have to find alternating current over a half cycle. Average value of AC over a half cycle. What is the average value of AC over a half cycle? Here I just write the definition. Actually, it is defined as the value of direct current which sends the same charge in a circuit in the same time as is sent by the given alternating current in half time period. Here we have to take I as it is equal to I naught sin omega t. Then we have I can be written as dq upon dt. As here we discuss about the charge, so no, same charge. So dq can be written as I dt, so, and then for half cycle means here we have to take the time limit from 0 to t by 2. So then just integrate the left hand side dq and RHS side I dt, and the limit of left hand side is from 0 to capital Q, and the limit of right hand side is as time changes here, so you have to take the half cycle. For half cycle you have to take 0 to t by 2. Okay, in place of I we can write I naught sin omega t, I naught sin omega t dt, that is from 0 to t by 2. Here we have I naught is constant, peak value take outside, then integration of 0 to t by 2 sin omega t dt. Let's just solve some. I naught, the integration of sin omega t is our minus cos omega t upon omega from 0 to t by 2. This becomes I naught by omega cos 0 minus cos omega capital T by 2. This becomes I naught, in place of omega you can write 2 pi upon t, yes or no, and then we have cos 0 is our 1, then minus cos, just write down in place of omega just 2 pi by capital T into t by 2. This becomes t I naught by 2 pi into 1 minus, if 2 is cancelled, then t, then cos pi is our minus 1. This becomes 2 to cancel, I naught by pi into t. This is our q. Q got I naught by pi into t. So current for half cycle, current for half cycle, I equal to q upon, for half cycle we have to take time t by 2. Okay, just remember this one, for half cycle we have to take the time t by 2, and this becomes I naught by pi into t upon t by 2. This becomes I, or in place we can write IAV also. I average is equal to 2 by pi I naught. Just remember this one, 2 by pi I naught. Okay, this also is the relation between average value of alternating current and peak value. I average equal to 2 by pi I naught. Similarly, we can get E average also. E average can be written as 2 by pi into E naught. Okay, then we have root mean square value of alternating current, that is called RMS value. Here we have to use heating eval, Joule's law of heating, H equal to I square RT, H equal to I square RT. We have to use this formula here. Okay, in place of I we have to write I naught sin omega to related. Here some definition is written. It is defined as that value of direct current which produces the same heating effect in a given resistor. Okay, as is produced by the given alternating current when passed for the same time, same if heating effect produced by both direct current and alternating current. Okay, so here we have to take from Joule's law, for small heating effect we can write dH. This is from Joule's law. dH can be written as I square R dt. Okay, and if capital T is our time period for AC, then the total heating effect produced H. H is our integration of dH, and here we have to take the integration of I square R dt, that is from complete cycle from 0 to T. Let it be equation 1. Let if I, you can write I effective, or you can also write IRMS is the effective value of SC. H can be written as IRMS square, okay, RT. Let it be equation 2. This is compare equation 1 and 2. Here you can get IRMS square RT, okay, from 1 and 2. IRMS square RT can be written as integration of 0 to capital T I square R dt. So our IRMS square becomes 1 by T, because R can be cancelled out, and integration of 0 to T I square dt. In place of I, you can write I naught sin omega t. So no, then just write down I naught sin omega t. Here this becomes 0 to T I naught square sin square omega t dt. As here we put I equal to I naught sin omega t. Then I naught is a peak value or constant, we can take outside I naught square upon t. Then integration of 0 to capital T sin square omega t dt. Yes or no? Then just solve this one. I naught square upon t integration of 0 to t. We can write sin square omega t as 1 minus cos 2 omega t upon 2 dt. If we split this integration into parts, then I naught square by 2 integration, 2t integration of 0 to t dt minus integration of 0 to t cos 2 omega t dt. Just here the second integration, just see the second integration. Here we have integration of cos over complete cycle, then this becomes 0. Yes or no? Then what you got here? I naught square by 2t into integration dt is a t. This becomes I naught square upon 2. Actually, this is our IRMS. Yes or no? This is our IRMS value. Okay. The IRMS is our I naught square by 2. Then what we got here? Sorry, this is not IRMS. This is our IRMS square. IRMS square. Okay. This is our I naught square by 2. Then what is our IRMS? IRMS is the square root of I naught square upon 2, and this becomes IRMS is our I naught upon root 2. Okay. This is also a relation between the RMS value and peak value of current. Or we can write also, if we divide 1 by root 2, then we can get 0.707, and then I naught. This is actually the RMS value of alternating current, which is 1 by root 2 times the peak value of its alternating current. Okay. Then we have root mean square value of an alternating EMF. We will discuss about the root mean square value of alternating current. Here we have to discuss root mean square value of alternating EMF. That means here we have to say also alternating voltage. Okay. It is defined as that value of steady voltage in RMS value of alternating current. It told about the steady current and alternating current. Here we have to discuss about steady voltage and alternating voltage or alternating EMF. That means in a given resistor, if we apply the direct voltage and alternating voltage for the same time, then they will produce same heating effect in that resistor. Okay. Then we have to derive the formula, or we can say here we have to derive the relation among the alternating EMF and peak value of EMF. Here also we can get ERMS equal to E naught by root 2. First of all, we have to take heat produced in a small time dt. In a small time dt, heat produced in the resistor is dH, can be written as I square R dt, yes or no? In place of I we can write E by R, or we can write E square by R dt. In place of E we can write E naught sin omega t. So from starting onwards we discuss about E equal to E naught sin omega t for alternating EMF. Then this becomes E naught square by R sin square omega t dt. For capital T time period, heat produced, integration of ds from 0 to h. In RHS side you can write integration of E naught square upon R sin square omega t dt, and the integration is from 0 to capital T. This becomes LHS becomes h. The RHS become E naught is our constant value, peak value. Then E naught square take outside, R also constant. Then integration of sin square omega t dt over 0 to capital T. This becomes E naught square by R. Here also we have to solve sin square omega t as 1 minus cos 2 omega t upon 2 dt. Here you have to take integration symbol. Okay. Then this becomes E naught square upon 2R into T. Okay. Then E naught square T upon 2R. Okay. Then what we have? If ERMS, if our ERMS is the root mean square value of the alternating EMF, then what we got here? H can be written as ERMS square ERMS square T by R. Let it be equation 1, this be equation 2. Here is our H. From equation 1 and 2, what we got here? From 1 and 2, get ERMS square upon R into T can be written as E naught square T by 2R, or we can write ERMS is our E naught upon root 2. Okay. Here also ERMS is 1 by root 2 times its peak value, or you can write ERMS is 0.707 times of E naught or peak value. That means E naught greater than ERMS greater than E average. Similarly, we can write I naught greater than IRMS greater than I average value. Okay, this is all about the lecture.